Okay, guys. So yesterday we were working through a conservation of momentum problem, and we ran tight on time. I asked you guys to finish it up. So let's do that real fast. Me too. Okay. I'll get you at the end of the hour. Okay, guys. So we were given all this information about the masses of the two objects, the velocities of the two objects. Hopefully, this problem should be familiar from last year. We did a gajillion of these. All right. The big thing I will caution you on, and this is true for both the 10-3 stuff we're doing now, as well as the impulse and momentum stuff that we did the other day. You got to watch your signs, okay? This velocity here is negative, okay? I've talked to a couple people about the 10-2 stuff that's due today, and the most common mistake I've seen is, oh, you forgot a negative. Oh, you forgot a negative, okay? So make sure you watch out for those, all right? So, this is an equation as long as you've just got two objects. I mean, this is kind of the deal, right? The total momentum before the two objects interact has to equal the total momentum after the two objects interact. Everybody cool with that? Yep. All right, so plug in your numbers. Did anybody figure out what the answer was? I hate you all.
I got -4, but
-4? All right, well, let's check it. So let's see. So total momentum before, 1250 times 5 minus 750 times 8. I guess I could have done it too. All right, so our total momentum before the collision is 250. That's got to equal, let's see, 1250 times the velocity of the truck final plus 750 times 7, 5250. So subtract 5,000, you get negative 5,000 equals 1250 VF. So I think I agree with Sebo that VF ends up being -4 meters a second. 1,000 extra credit for Sebo for doing the one little thing I asked you to do. A plus, you can stop coming to class. All right, everybody good? Okay, now, so let's do this. The question also asked us to determine what kind of collision it is. So what am I asking you to do? Identify if it's elastic, inelastic, or completely inelastic. All right? So, let's review real quick. Completely inelastic would mean that the objects stick together. What would be true about their final velocities if they stick together, you guys?
Be the same.
They'd be the same. Do the two objects have the same final velocity?
No.
No. So it is not completely inelastic. All right? So now we just have to decide if it's elastic or inelastic. Okay? The difference is this. In an elastic collision, all the kinetic energy is conserved. So what do I need to do here to figure this out, you guys? Find the total kinetic energy before the collision, find the total kinetic energy after the collision, and compare. Good? All right, so let's do that. Oops. Okay, so we just found this velocity. It ended up being -4 meters a second, right? So basically all I'm going to do is I'm going to find the total kinetic energy before the two objects interact, find the total kinetic energy after the objects interact, and see if they're equal to each other. That's terrible notation, but the equal sign of the question mark means maybe equal. All right. Do I need to go through these calculations, you guys? No. It's just 1/2 mv squared plus 1/2 mv squared on one side, 1/2 mv squared plus 1/2 mv squared on the other side. Cool? All right, and I don't remember exactly what the numbers are, but what you end up finding out is that the total kinetic energy before the collision is greater than the total kinetic energy after the collision. So, what does that mean? It means it's inelastic, right? But not completely inelastic. Is that cool?
Yep.
Is anybody stewing about the fact that I didn't calculate?
No, but how is that like possible?
Okay, so where did the energy go?
Yeah.
Heat, friction, sound, deformation of the two objects that are colliding. Everybody good? Deformation? I don't know the proper word to say that. All right. Now, is it possible that could we ever have this?
No.
Not unless what? Unless there's some sort of external force. So like, suppose that you had stored energy in a spring. And when the two objects collided, the spring, boom, did that. That would be adding energy, right? Okay? Or an explosion. There's a problem in the book somewhere about, there's a little bit of gunpowder, and they collide and the gunpowder explodes. Okay? Yeah, totally. Yeah. Thank you, right. So, if, you all set? Okay, cool. So, if you ever have a situation where you gain energy as a result of the collision, that means there must have been some sort of stored energy in your objects. Follow? All right, any problems with this? Okay. Cool. So, example number 2. So this one tells us that it's a completely inelastic collision. So we're doing the same problem again, but this time it tells us it's a completely inelastic collision. I'm a third grader. What does completely inelastic mean? It means they stick together. So what that means for us in terms of our problem solving is it means that the velocity of the truck final is equal to the velocity of the car final. So I don't need to distinguish between the two final velocities. So let's just call them both VF. Follow? Am I going too quick? Are we good? Okay, so my drawing, I'm going to cheat. Okay, so we've got the same initial information. The only thing is they stick together. And our question is, what's the final velocity that they have after they stick together? Cool? All right, so the setup for solving this is exactly the same. You're going to go, oh, well, the total momentum before they collide has got to equal the total momentum after they collide, right? So that means the mass of the car times the velocity of the car initially plus the mass of the truck times the velocity of the truck initially equals the mass of the car times VF. Notice I don't need to distinguish between the car and the truck, so I just called it VF. Plus the mass of the truck times VF. Is there another way I could write this, you guys? I guess all I was trying to get at is we could think, since the car and the truck are stuck together, we can kind of treat them as one object. Sometimes people find that to be useful. Does that make sense?
Yeah.
All right, so solve it. So this ends up being 250, just by plugging in your numbers. I'm being sloppy. What are the units here? What are the units for momentum? Kilogram meters per second. Newton seconds is acceptable, but a little, technically they're equal, but kilogram meters per second is sort of the accepted way to write that. Okay? Equals, let's see, what's our total mass? 2,000. Oh, that's nice. 2,000. Who wrote this problem? Yeah. Cool? So then divide both sides, and your VF turns out to be whatever an eighth is, so 0.125. And notice it's positive, which has significance. Why do I care that it's positive?
It's going right.
It means it's going to the right. Okay? Incidentally, if you care, this also happens to be the velocity of the center of mass. Think about that for a minute. Why would that be true? Why does that have to be the velocity of the center of mass? Give everybody a second, and then I'll get you, Peter. All right, what are you thinking?
Is it because they're moving as one object? So since the entire system is moving at like the same constant velocity, that means that the center of mass also has to be moving at that constant velocity?
Yes, 100%. Talk to me about before the collision. What should the velocity of the center of mass be before the collision, you guys?
Oh wait, wouldn't it be the same?
Yeah, why is it the same?
Because like the mass of the system doesn't change, right? So then like it just, I don't know. It makes sense in my head.
All right, let's see if we can figure out why. What do you got? Yeah, there's no external forces, right? The only two forces are the forces of the two cars pushing each other, right? Cool? All right. Any problems with that one? Okay. So at this point, I guess a couple comments just to be aware of. So note, we could find, if we wanted to, and I will go through these calculations if anybody wants me to, but we could find the change in total kinetic energy. Oh, why did I write find twice?
I like it. No, I like it.
All right. All right, so do you guys all agree we can find the change in kinetic energy? Okay, we could, if we wanted to, find the change in momentum for the car. We could also, if we wanted to, find the change in momentum for the truck. Do you guys agree that we can find those two things? Just do mass times change in velocity for each of the individual objects? What would be true about those two numbers? What would be true about those two changes in momentum? Yeah, they'd be equal and opposite, right? Because the car is going to lose momentum. Since the total has to stay the same, that means it must be transferred to the other object, right? So these are equal and opposite. Clear? Any problems? Anything else we want to find?
That's fine for.
Okay. Elastic collisions have a special property. This we did not learn last year. I highly recommend you write this down. All right. So the book gives you, I'm going to skip ahead for half a second and then come back. The book gives you these crazy equations. I've never memorized those. They're a thing. But A, there's no way you're going to remember those two equations when you get to the AP test. B, they only work if one of your objects starts at rest. Okay? So, as a result, I find that what I'm about to show you here is a much more useful thing. Okay? What I'm about to show you is not written on the AP sheet. You might make a mental note of it so that when you're studying for the AP test, like, remind yourself, this isn't on the sheet. This might be useful. Okay? So, I'm going to go through a whole bunch of algebra. Are you ready? Here we go. So, it is true that in any collision, let's see, which way do I want to write this? It is true that in any collision, if you've got two objects, your change in momentum for one of your objects is equal and opposite to the change in momentum for the other object. Yes? Okay? So that means that the mass of object A times the velocity of A final minus the velocity of A initial is equal to the mass of B times, and then instead of putting a negative sign in front of it, I'm going to just switch the order of these two dudes to give me the velocity of B initial minus the velocity of B final. Does that make sense?
Yeah.
All right, so that is useful equation number 1. It is so useful that I will highlight it with this lovely yellow color. Lovely. Wait, you just did just say. Okay. All right, so everybody good with that? All right, now. In an elastic collision, what property defines an elastic collision, you guys? Bouncing, more than that. No energy lost. So that means that my total kinetic energy before the collision has got to equal my total kinetic energy after the collision, yes? Follow? All right, so total kinetic energy. All right, well that means the kinetic energy of object A before the collision plus the kinetic energy of B before the collision. So let's write that out. This is 1/2 the mass of A times the velocity of A initially squared plus 1/2 the mass of A times the velocity of A final squared. So that's the left side of the equation. Because I'm stupid? That's totally wrong. Thank you. Try that again. Mass, oh, fiddle faddle. Mass of, that was funny, of B times the velocity of B initial squared. Sorry. Thank you for catching that. All right. Everybody good now? We want to add all the initial kinetic energies. Follow? Do we need a second? Everybody caught up? All right. Equals, I'm going to do the same thing for final, right? So 1/2 the mass of A times the velocity of A final squared plus 1/2 mass of B times the velocity of B final squared. Cool? Everybody good? Super fun. All right, so first of all, let's multiply everything by 2. That gets rid of the 1/2s. Cool? And now what I'm going to do is I'm going to group it. So right now I've got it set up so that all the initials are on one side and all the finals are on the other. I'm going to rearrange it to get it so I've got all the A's on one side and all the B's on the other. Good? Yep. All right. So if you do that, let's see, I'm going to have to subtract VA final from this side and subtract VB initial from this side, right? So I'm going to get this. Mass of A times the velocity. Oh, shoot. I'm going to do it the other way around. No, I am going to put all the A's and B's on the same side, but I'm going to subtract V8. I'm going to move here. I'm going to move this one to the other side, and I'm going to move this one to the other side. Follow? For reasons that will be apparent in a minute. So I'm going to get mass of A times velocity of A final squared minus mass of A times velocity of A initial squared equals mass of B times velocity of B initial squared minus mass of B velocity of B final squared. Okay, so sorry, I sort of made a little bit of a mess of that, but basically I rearranged stuff. Cool? Any problems? Yay, algebra. All right, so now I'm going to factor out my masses. So I get mass of A times velocity of A final squared minus velocity of A initial squared. And over here, I got mass of B times velocity of B initial squared minus velocity of B final squared. We're almost done, I promise.
Yeah.
I know, I'm with you.
I wasn't paying attention, that's why I don't know what's going on.
Cool, well, I hope I don't put this on the test.
Oof.
Is it recorded? That'd be great.
All right, everybody good? Somebody tell me something algebraically useful about this expression.
Mr. Hager, you want to record the notes?
It is recorded.
Oh, sweet. I didn't see it.
Oh, it is 2a delta x. That's not what I was looking for. Something else. Algebra. Difference of squares. Thank you, Johnny Walton. It is a difference of squares.
Yes.
So this becomes. Oh. Sorry, I didn't mean to change colors on you. So this becomes mass of A times velocity of A final minus velocity of A initial times velocity of A final plus velocity of A initial. I know, I'm sorry. I usually don't go through the algebra on this stuff, but I feel like this one's important. I don't know why. I just do. To be fair. All right, and then on the other side, you're going to get velocity of B initial minus velocity of B final times velocity of B initial plus velocity of B final. All right, we are 99% done. All right, so is everybody up to where we're at? Okay, go back up and look at the lovely yellow. Look at the lovely yellow. It's you should be looking at the lovely yellow, which you hopefully wrote down. The lovely yellow tells us that this is equal to this. So what do? They cancel. So in an elastic collision, it turns out that if you take the initial velocity and the final velocity for both of your objects and add them up, it's equal. Oops. Oh my gosh. Fraser, I agree. No longer lovely. All right. So, when you are doing the homework for whatever section this is, I think it's 10-4, right? When you're doing the homework for this section, or maybe it's 10-3, I don't know. I've gotten them mixed up. When you're doing the homework for this, if the problem says two objects collide elastically, or an elastic collision occurs, or something, you're going to need to think system of equations. Because now we know two things. We know momentum is conserved, and we know this. All right? So what I remember last year what happened was I had a lot of students that anytime I gave them an elastic problem, they would go, oh, well, that means momentum is conserved and energy is conserved. And they'd get these two huge equations, one for momentum and one for energy. All right? But what I'm saying is you don't have to do that. That giant energy equation gets replaced by this. Okay? Now, what does this mean? Absolutely nothing. Okay? This really has no significant meaning. Okay? Do you know what I mean? Like, does it make sense to add an initial and a final velocity? Yes. Like, if I'm driving at 10 meters a second and then I speed up to 20 meters a second, is there any significance to 30 meters a second? Like, does it mean anything? No. Okay? So, this is how I always remember it. If you would prefer to remember it this way, you can also do this. If you rearrange this, if you now flip stuff around to get all your initials on one side and finals on the other, you end up getting... Why am I dumb? It's the change in velocities are equal and opposite, I think, right? So VA final... Oh, no, it's not even the changes in velocity. So never mind. There's no way to make sense of that. right.
The differences between the two objects' velocities that are constant.
Yeah, no, yeah. Yeah. Okay, so anyway, so that's the thing. Cool? So, let's see if we can use this to solve a problem. All right, so again, so if you take the algebra a little bit further, if you put VBI as 0 in, if you put VBI of 0 into those two equations I just showed you, you can come up with this. I almost never use those, okay? I don't think I assigned you any problems where I expect that you would use either of those equations. Okay, but they're there if you want them, all right? They're in most books. I don't know, I've never found much use in them just because they're long equations that I can't imagine you'd memorize. Whereas this, to me, you could memorize. That bottom equation. Okay, all right, so before we get to a problem, let me show you guys a couple special elastic collisions where your initial velocity of one of your objects is 0. Okay? So, number 1 is this. If you've got two objects that have equal masses, yeah, they do look like M&Ms, I agree. Okay, so if you've got two objects that have equal masses and one of them is initially at rest, if the collision is elastic, then what will happen is the one object will move into the stationary object, the moving object will stop, and the stationary object will begin moving at the same velocity that the other one began with. Like pool. Exactly like pool. Okay? So if you want to see it, it's this. Here's these two parts have equal masses. This one is stationary-ish. I tried so hard to get this track level. So, cool. So if that had been perfectly elastic, this would have stopped, and that would have continued along at the same velocity the other one began with, right? Why did I not get these out? Hold on. Who locked that?
You did.
Yeah, I know. No, swinging wonder. No, it's tangled. Oh no. So you guys have all seen these before, yeah? No.
Well, what's the actual name of
This is technically called Newton's cradle, is like the sciencey name for this. Or you can call it a swinging wonder. All right, so look, you guys. So when this swings down, it gains kinetic energy and it gains velocity, right? This is very close to an elastic collision. Okay, so one stops and the other one comes out the other end, right? Okay, so this is actually demonstrating both conservation of momentum and conservation of energy. Okay, if I do two of them, then you get two of them out. I'm going to not make the obvious joke because I'm recording. All right. So if I do two of them, you get two of them out. All right. If I do three of them, you get three of them out. All right, etc. Right?
Whoa. That's cool.
Seriously, you guys have never seen that before?
What if you do 5 of them?
All right. All right. Now, important question. So the premise is for sure momentum needs to be conserved because that's true in any collision. All right, and then theoretically energy is conserved. Technically we're losing a little bit because you can hear it. Okay. Now, when I pull one out, then you get one out on the other end, right? Okay. So mass times velocity equals mass times velocity, right? All right. Now here's my question. If I pull two of them out, then I get two out on the other side, right? So 2m times v equals 2m times v, right? Why don't I get, you got 2m times v, right? Why don't I just get one coming out at twice the velocity? Stop and think. Actually, better yet, talk to whoever's sitting next to you. Why doesn't that happen? There's a very... The question is, The question is, if I drop 2, why don't I get 1 coming out at twice the velocity? Wouldn't that be the same momentum?
I figured it out. Because the one was
Ideas? Anybody have an idea for why? What do you got, Evan?
Something about the center of mass or no?
No. The center of mass of the system is pretty complicated because there's a lot of forces. There's gravity. There's the centripetal force from the tension of the the ropes. So yeah, it doesn't have to do that. Molly, you got an idea?
What do you have to do with the special code we just learned, or like the velocities?
Indirectly, yes. That your velocities have to add up, right? So if you want to look at the property we just learned, you would have to have, so let's suppose that the marble coming in goes in with a velocity of 2. Okay? So the velocity of A initially is 2. Its final velocity is 0. That's got to equal the initial velocity of the other one plus something. It's got to be 2, right? Okay? So yeah, 100%. That's not what I was thinking of, but yes. Anybody come up with another reason? All right, so let's suppose that that happened. Let's suppose that we had the marble coming in. You've got a mass of 2m moving at a velocity of v, right? So that's 2 marbles coming in, right? And then suppose we had 1 marble coming out with a momentum or a velocity of 2v. Do you guys agree that that would be conservation of momentum? All right. Let's look at the energy. Let's look at the energy. This thing would have a kinetic energy of 1/2 mass times velocity squared, right? So that would be mv squared, right? Over here, I would get 1/2 m times 2v squared, which is 2mv squared. Talk to me.
Conservation of energy.
You can't gain energy. The only way for this thing to conserve both momentum and energy is to have an equal amount of mass come out on the other side. You can't have more mass come out on the other side. Okay? Does that make sense, you guys? So really quick, here's 4, and then we'll put this away.
Can we try with 5, Mr. Hanks?
always the negative, Joe.
Oh.
Okay, good? All right.
And that's what we make
All right, so we looked at this. All right, this next one is a little tougher to show, but the idea is if you've got an object that is very, 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 very large relative to the other object that's at rest, and this actually requires a fair amount of limits and stuff to prove it, but it turns out that during the collision, the large object, the amount that it slows down is insignificant. Okay, so it basically continues along at a velocity of v, okay, as this mass goes to infinity. The smaller object will move at a velocity that's twice as big as the initial velocity of the other thing. Okay, so I don't know that I can exactly show you that, but I'll give you an approximation of it by piling a whole bunch of mass on one of these carts over here. So this one's 500 grams right now, this one's 1,000, 1,500, 2,000,
Come underneath the track itself.
Thank you.
No problem.
2,500. All right.
I mean, wait,
Is the
All right.
track going to get pushed off?
Oh, shoot. I don't think so. I think it'll be okay. All right, so here we go.
wait.
So this one, so what this is telling us is the amount that this one slows down is going to be insignificant, and this one is going to go at a velocity twice as big as this one. Cool? All right, questions on that? All right. Shh. The question was, how much bigger does bigger have to be? The problem will make it very, very clear. I wouldn't use this as a problem-solving strategy. I would use it as like, you know, a truck hits a super ball.
No, I don't think so.
Like a little rubber ball, like you get a bouncy ball.
Okay, I was just thinking, like, why is it two if their mass is going to be such different ratios?
So the explanation behind this requires some fairly advanced limits. Watch the language and everything. If you want to see it, I'm happy to show you. I don't know that I want to spend time on it right now. I already killed you guys with all that other algebra. So if you want to see it, I'm happy to show you. I'd have to sit down and figure it out. Here's the answer. It comes from these two equations. If you set, as you make the mass of A go to infinity, these guys cancel out, this is insignificant, and you get 2 times VAI. There's your answer. That is a further algebra from all this algebra we did here. Okay? Shh. All right. Now, this one, you guys. All right, so this one does not come up that often. All right? The one that comes up a lot is this one, number 3, where you flip it. So instead of having the super large object moving into a stationary little object, flip it around. So you've got a super small object colliding with a stationary super big object. Okay? This would be a bouncy ball hitting the Earth. Okay? For that collision to occur and energy to be conserved, the idea is the bouncy ball is going to come in with some velocity. If the collision is perfectly elastic, it'll bounce back at exactly that same velocity. Okay? All right. And then finally, the last chunk of notes, which we'll do here at some point, probably not today based on the time we've got left, is if you do it two-dimensionally, so if you offset one of them slightly, so that this one comes in, you can see it's going to hit at a weird angle, right? So it turns out that so this one is at rest. So it turns out that the two balls after the collision, their velocities will be perpendicular. Okay? So that's totally, a billiards thing, right? The ball comes in, and then it bounces off. The ball you shot is going to move at a velocity perpendicular to the ball you hit.
Is there anything, like, how do we figure out the magnitude to such velocity?
Say that again?
Like, how do we figure out the magnitude?
That we'll get to. We'll get to that. All right, so are we good? All right, so we have just enough time to do this last problem that's elastic. All right, so here's our setup. Oh. All right, so here's our setup. We've got these same two vehicles colliding again, but this time, oh my gosh, stupid smartboard. There we go. Okay, but this time our collision is elastic. Okay? So, notice there are two unknowns here. We know the velocity of the truck before the collision. We know the velocity of the car before the collision. We need to find both of the final velocities. Okay? So there's two unknowns. How many equations do we need? Two equations. All right? So equation number 1 tells us it's elastic, right? So now we can use that special property for elastic collisions. That tells us that if I take the velocity of A initially and the velocity of A final and add them, I get the same thing as if I do the velocity of B initially plus the velocity of B final, right? Make sense? So I can plug in my numbers. So the velocity of A initial, so I've got 5 plus the velocity of the truck initially equals -8 plus the velocity of the car final. Oh, shoot, this is supposed to be final too. Sorry, my bad. Final. All right, so there's equation number 1. Good? All right, so my recommendation is solve this for one of the two variables. So let's add the 8 to both sides, and I get this. The velocity of the car final is the velocity of the truck final plus 13. So there's one of my two equations. This says 13, not 8. Oh, man. 13. 8 plus 5?
Oh, sorry, I didn't see that.
You okay? All right, everybody good up to there? Yes. All right, where am I going to get equation number 2?
Any collision.
Any collision means that our total momentum before the collision has got to equal our total momentum after the collision, right? So the mass of... So let's see, the mass of the truck, so I'm going to get 1250 times 5 plus 750 times -8 equals 1250 times the velocity of the truck final plus 750 times the velocity of the car final. So now I've got two equations, two unknowns. Plug VCF in over here and solve for VTF. Does that make sense, you guys?
Yes. Yes.
Okay, so that's, algebra, whatever, 3. What algebra class that is. Cool? All right, we don't have time to solve it right now. The bell's going to ring here in a minute. But you guys can finish that, obviously, yeah? All right, questions, you guys? All right, so we're really done with most of the notes. The only thing that we need to do, and this will be like maybe 10 minutes, is do this two-dimensional collisions. Basically, just do it component-wise. You split everything up into your momentum in the x direction, momentum in the y direction, and then it's all exactly the same. All right? So I'll do an example of that one day next week. All right? So 10-2, do next time I see you. 10-3, do the time after that. 10-4, the time after that. Is there a 10-5?
There is.
Okay, 10-5, the time after that. And then test either Thursday or Friday. Oh, hey guys, one other quick